This screencast is on relative velocity. I wanted to just start right away with the problem we saw before, where we didn't really talk about it. It was kind of tucked in. This is the one with Alice and Bob, and they're 300 miles apart on the same straight highway. We didn't really need to use it if we were careful with the coordinate system and we wanted to use two equations of motion. We're going to go back to this one in a bit. But let me just remind you what the problem is, and we'll see how in one dimension with not a lot of things moving, relative velocity is pretty easy to do in our heads intuitively, but it can get harder in two dimensions, and it certainly gets harder in one dimension when there's more than one thing moving at respect to the next. So let's remind ourselves what this problem was. We had Alice and Bob. So VA is for Alice, VB is for Bob. Why don't I just label those points? So we have Alice and we have Bob, and they are 300 miles apart. And it's the weekend. It's time to get together. They want to get together as fast as they can. So they're gonna, on the same highway, they're gonna head towards each other. Alice is moving at, well, first we need to define a coordinate system. So let's do that. Let's pick another color here. So we're gonna say that where I drew the blue here, it's getting a little, this is our 0 mark right here. So this is 0. And we actually need to define some positive and negative directions here. We're gonna say to the right is positive, and so to the left is negative. We don't have another dimension, so we don't have to worry about up and down in this problem. And then if you recall from that last problem, that last screencast, VA, I have it as a vector because really it's in the positive x direction, but VA, the magnitude of the velocity here we had was 80 miles per hour. And then for Bob, Bob's still going fast, but he's going slower. V of Bob is equal to 70 miles per hour. And you know what, why don't I just keep the vector there, because this is important here. We're going to define it as minus 70 miles per hour, and that already gives us the vector notation. If I do the magnitude, it takes the minus off. So this is a vector here. It's implied that the minus 70 means to the left in the x direction, and the positive here. So let me put those vector signs back just to be very careful. And then I was using a notation on the notes the other day where I actually put like an x hat and a y hat. I like that a lot. That's just shorthand for in the x direction. You know, why don't we do that too? Let's get used to that. Your book doesn't do that. They think that this is too hard to do, but all that means is in the x direction. So that words means in the x direction, and it just saves me space to write. So likewise then, Bob's would be also, the minus tells me that it's minus in the x direction, so that x there for Bob also means in the x direction. I think we can handle that. If you don't like it, you can ignore it. This positive means to the right, and this negative means to the left. Okay, so this is the picture from the other slide. It's just a little smaller, so we have more room to write. And remember, in the problem, we wanted to know the time it takes for them to meet each other if they're going at these speeds. One of the ways we could have solved the problem was talking about relative velocity, and it kind of was implicit in the problem without us having to talk about it. We could say Alice thinks she's the center of the universe here. And so these speeds here that we have 80 and 70 here, they're really defined at respect to the road. We didn't say that in the problem, but they're Bob at respect to the road and Alice at respect to the road, knowing that to the left is minus and knowing that to the right is positive. We didn't say that language because we didn't really need to, but now we're going to be a little more careful here. So if I say V Bob at respect to Alice, how fast is Bob moving as Alice sees Bob in her own center of the universe? So if the script that comes after here, it's an A, means that Alice thinks she's the center. Everything's coming to her. She's not moving at all. And so in that sense, to her, it looks like Bob is going to the left. She's coming so towards her in the system we defined. We defined the left is negative, the right is positive. To the left is negative, and it looks like he's going really fast. It looks like he's going 70 plus 80 miles per hour. So that's going to be equal 150. It's minus, because it's to the left, miles per hour. We could also say, oh, but Bob thinks he's the center of the universe here. So again, the B, because it comes second, that means this is from Bob's point of view. So Bob is not moving now, but he thinks Alice is coming to him. And so again, the speed is their speed combined. It's kind of, it's like she's coming both 70 and 80 miles per hour combined, but he agrees that if in this coordinate system we defined to the right is positive, so he would see that equal to 150 miles per hour. Okay, let's make those a little bit smaller here. So we have some room to write. Okay, now the way I did this wasn't very technical here. I did it by intuition. And this might be something that you can do pretty easily in one dimension, and it's fine, but here's the way that I should have done it. The way that I should have set this up was I should have defined their velocities relative to the road, and then I could define their velocities relative to each other. So again, what I said before, this is implied, should have said so in the problem to begin with. This is 80 relative to the road and minus 70 miles per hour relative to the road. So let's write that out here. So I know that v of Alice, I really should say relative to the road. Okay, and that's equal to the 80 miles per hour. And v of Bob relative to the road is minus 70 miles per hour. And now there's a cool trick that I can do if I want to find one relative to the other. Move that over here. Let's move these a little bit out of the way. So if I want to find out of, again, now we're in Alice's world, Bob relative to Alice, that's going to be equal to v of Bob relative to the road plus, vector addition. Sound familiar? This is what we were talking about in class and talking about for the last couple of lessons. And v of, okay, I need road relative to Alice. And then let's just take a minute and look at this notation here. All right, this one I need to figure out what this is. I'm going to tell you that's in a bit. But you see how the r's are here? These r's, the way I've set it up, they sort of cancel each other out. So I can arrange vector addition, if this is true, if I have Bob relative to the road and road relative to Alice, the r's cancel out and they just leave me b to a here. Okay, and that's what I wanted. So then there's another clue that you need here. And the cool thing about the way we've written Alice relative to the road, Bob relative to the road, is if we change these order here, we just make this a minus sign. So let's write this now. So v of the road relative to Alice is just going to be a minus 80 miles per hour. And then v of the road relative to Bob is equal to 70 miles per hour. And this is sort of a funny way. This is, again, Alice again thinks she's the center of the universe, and the road is moving backwards to her, right? So if she's here, she can say, hey, look, I'm still, and the road is coming closer to me. You know, this is a new piece of road she's going to get to. That's how we would say it. But she said, no, 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 I'm still, and this piece of road is moving this way until it gets to me. Likewise, Bobby could say, no, no, I'm still, and this piece of road is getting closer to me at a positive 70 miles per hour. Let me box the main equation that we have here. So this is the equation that we're interested in. And once again, we want to set it up so road cancels each other out and it leaves a B and an A. Let's see what this gets then. Using our sign convention is what we know how we can, if we change the order here, we just change the sign. Change the order here, you change the sign. Okay, so now I've cheated a little bit. I squeezed in an R here to let us know that when we define these initially, this was Alice relative to the road and Bob relative to the road. And now remember what I could do, Bob relative to the road is minus 70, but road relative to Bob, this flips. So let's write that out. So this is going to be equal to 80 miles per hour, because that's just Alice relative to the road, but the road relative to Bob is going to be plus 70. And so that is equal to 150 miles per hour. Cool. And that's what we expected before. So if Bob here is at the center of the universe, to him it looks like Alice is coming at a speed that's the sum of these. And the reason it's positive is because to him, she's coming this way to the right. and that's the positive direction. If we did the other way around, if Alice is the center of the universe, Bob is coming to her, and again it looks like he is coming at a speed that's the sum, but because it's in the left direction, it would be negative. Okay, so let's solve the problem of how long it takes for them to meet each other, but we're going to use relative velocities, which is different from the way the other screencast shows you. So we're going to do it in the coordinate again where Bob thinks he's the center of the universe. And remember, there's an equation. One of the kinematic equations is x equals x naught plus vt, but we're going to do it in this relative coordinate and this relative velocity system. So the way I'm going to write it in this time is I'm going to write x AB is going to be equal to x naught AB. I'm just going to robotically write it down, being very careful with all my ABs. V AB T. This is just that same kinematic equation. There's no acceleration. So we have x plus Vt is equal to the final, or the position at that time t. So let's look at that. This is the position at that time t is where I started with, the velocity I'm going times time. But now, this is a little more complicated. This is in Bob's world. So the final position we want here, the time that we want the position for, is where Alice is at the same place as Bob. All right, so we want Alice to be at Bob, so that means that's going to be equal to 0. So that's a 0. And then where does Alice start at respect to Bob? That's what this is saying. Alice at respect to Bob, and where are we starting? Well, she starts, because he's the center of the universe, minus 300 away now. So let's write that in. Minus 300 miles. And then we solve this on the other page, and it's up here on the right. I just copied it down. We know that in Bob's perspective, it looks like Alice is coming towards him at a 150 miles per hour to the right. So we'll write that in. 150 miles per hour. It's positive, it's to the right. And that's supposed to be a t there. Good. So now all we need to do is we need to solve for t. Let's start with the simple algebraic equation. Let's get the 300 to the other side. So to get to the other side, I add 300 both sides. I'm going to get 300 miles is going to be equal to 150 miles per hour times time. Let's make this a little smaller. Oh, there we go. Okay, and this is a simple algebraic equation, but why don't we solve it together? To just be careful with our algebra, I'm going to go up there to give a little more room. And then if I want to get t by itself, I need to divide by 150 miles per hour, both sides by 150 miles per hour. So being careful with units, I'm going to say 300 miles divided by 150 miles per hour is going to equal t. And maybe some of you can already see that this is going to be 2 hours, but let's just be extra careful. So I'm going to go 300 divided by 150. I'm going to put the numbers on one fraction, and then I'm going to do miles divided by miles per hour. And I know that that's going to equal 300 over 150. That's 2. And the miles divided by the miles per hour, that's going to be miles. And I have to multiply by the reciprocal. So that's going to be hour per mile. And then boom, boom, and I'm left with 2 hours. And if you remember, that's what we got last time. And we can check that in 2 hours. We know that Alice is going to be, at least the original coordinate system we drew, she's going to be 160 miles from the original coordinate system, and Bob is going to be 140 miles, and that's going to add 300. But in our new coordinate system, 2 hours at 150 miles, 300. It's just one shot. So if you want to go back and see how we did it before, I urge you to go back and look at the other screencasts. And if you remember, we had to use 2 equations because we had this coordinate system at respect to the road, and we weren't doing relative velocities. We had an equation for Alice, an equation for Bob, and then we subtracted one from the other, and then we solved. It actually is a little more complicated algebraically. So if we get used to this method of relative velocities, we can actually make the math a lot easier. But because this is new, maybe this seems more complicated now. But these are 2 ways to do the same problem. In each case, we need to keep track of directions. We need to keep track of where we put our origin. But this is the method of relative velocities, but for one dimension.